Alright, good morning, guys. So, my presentation today is the last part of Chapter 9. It's just an extension of what we've already discussed, or a continuation, really. And my sections are sections 9.5 through 9.8, and it's just going to continue talking about drug metabolism. So, getting started, section 9.5 talks about phase 2 metabolic routes, and these are also known as conjugation reactions, and they often represent the final step in the metabolic pathway of a drug before it is excreted from the body. And it's called these conjugation reactions because the products are conjugates of the drug after it was broken down and stuff like that. And usually these conjugates are pharmacologically inactive, meaning they will have no effect on the body, unless, of course, they build up to toxic extents and they won't be excreted, but the products themselves will not see the same pharmacologic effect as the drug does. And there are many different reactions that are commonly involved in these phase 2 metabolic routes, and they're seen on page 191, and they are acylation, sulfate formation, methylation, and also conjugation with other compounds. And the book goes more in depth on these reactions and kind of what they are and some more details of them. So moving on to section 9.6, the pharmacokinetics of metabolites. The variable used in this is the total administered drug, and this is represented by the letter A. And these pharmacokinetics are important to be studied by looking at the metabolic pathway and determining if or where there's a rate-limiting step, because this rate-limiting step is going to be kind of the bottleneck, so to say, of how our bodies will get rid of the drug. So this rate limiting step is where our body this is what determines how fast the product will be broken down and excreted. So if it's a very slow rate limiting step, then at that point it'll take a while, and at that point that's where the drug would build up to toxic levels because it would take so long to be excreted. And the pharmacokinetics, this is measured in humans by administering the drug and measuring the concentration of the drug metabolite in the plasma. And this can be only partly metabolized in some cases when measured. And sometimes the drug is not broken down, but it is just excreted as the drug itself. And other time it's broken down into metabolites. So the metabolites that are seen here represent only a fraction of what's produced by the body. And a good diagram of this is on page 192, and we can see down here on the left, this is the drug administered over here, and the rate constant. Sometimes the drug is eliminated by itself through other routes besides breaking down, like excretion and stuff that we've already talked about. And then other times the drug can be broken into a metabolite, and then this is then eliminated from the body. So the equation that is used for all this stuff, all this fancy stuff, is seen here at the title. And there's a lot to it, but the gist of it is the K, the KF, and KM here. And this kind of determines where, or not really where, but if the drug will build up to toxic levels or if it'll be broken down into metabolites and excreted. So we can see here where K is greater than Km, the metabolite is accumulated in the body and it will not be excreted fast. And then in other cases where Km is greater than K, the metabolite will be eliminated from the body, and this is represented on page 193 in the picture in the book. So the first picture on the left is representative of K being greater than Km. So you can see that the concentration of the drug will go down in the body, but the metabolite will remain pretty constant. So that shows that as the drug is finished doing its thing, the metabolite will build up, and then over here on the right, the drug and the metabolite will both be eliminated together, and the metabolite is much lower concentration than the drug, so the metabolite is excreted and does not build up after the drug is kind of finished, and that's where Km is greater than K is seen. So moving on to section 9.7, drug metabolism and drug design. So obviously different drug structures have different metabolism, and this is based on the structural changes. And so some of these changes the drug can be more stable, and let me rephrase that. The structural changes can be one of two. The drug can either be more stable, or the structural changes can increase the metabolism of the drug, also known as being less stable. So these structural changes, they are hard to predict, just like other drug designs and the effects of it. It's better seen through testing, and that's with anything. A computer can't do everything for you. And of course, the goal when changing the structure of the drug for different metabolism routes is not to change the pharmacological effects of the drug, because then that would be changing the drug itself and changing what it does, which is exactly what we don't want to do. So, if you want to increase metabolic stability of the drug, you will replace a more reactive group with a less reactive group, making it more stable and less likely to be broken down by the body, keeping the drug in the body longer. And an example of this is dealkylation and or switching an ester group with an amide group. And then if you go the other way and want to decrease metabolic stability, then this is replacing a less reactive group with a more reactive group, and this will prevent the drug from being in the body for a long time because it's more reactive, and it'll be easier for the body to break it down. So an example of this is the exact opposite of before. So you can alkylate something, or you can switch an amide group with an ester group. And then the last section that we'll talk about is 9.8, which are prodrugs. And we've already talked about this pretty much. And basically, prodrugs are biologically inactive compounds that are metabolized into an active metabolite. So whenever you take a prodrug, you're not actually taking the drug, but your body will break that down, and its metabolite will be the actual drug itself that you'll see an effect from. So these prodrugs can be broken down into two categories, and these are bioprecursor prodrugs and carrier prodrugs. So the bioprecursor prodrugs are kind of your old-fashioned classic prodrugs where the molecule that you take is the inactive form, and your body will break it down into the prodrug. And this is mainly keeping the drug inactive until a certain point. And then also there are carrier prodrugs, and the carrier prodrugs are where the active drug is attached to a carrier compound that will help with various different things. And this is then broken down into the active drug. So some of the things that the carrier prodrugs are used for, you can use to increase absorption through the membranes. And this is looked at the hydrophilic-lipophilic nature balance. So we know that if it's too lipophilic, it'll get in the membrane, but it will stay in the membrane. And if it's too hydrophilic, it won't want to go through the membrane, and it'll want to stay in the aqueous environment. So different carrier things you can attach to that will help change that. They're also used to reduce the toxicity of the drug, and this is from the metabolites being excreted faster. So different carrier compounds can help it be broke down faster or slower depending on what you want and how the toxicity levels are. And also patient acceptance of the drug. This isn't something that we've really touched on, and it's not really thought about a whole lot, I don't think, but it's extremely important, I think, and this is really the odor and the taste of the drug. You know, how many people would want to take a extremely nasty drug, especially kids, and younger people who are sensitive to taste and things like that. So if you can make it less smelly or make it taste better or whatever without changing the effect of the drug, then why not? Why not? It's a great thing. And then also, like we mentioned earlier, you can slow the rate of release of the drug, and this is basically the prodrug being harder to be broken down by the body, so it'll stay in the system longer. And the book talks about how an amide and ester-linked fatty acid carriers are good for a slow-release drug. They take a long time to get broken down. And then lastly, some of these have also been designed to be site-specific. So a thing about drugs is not always do we want the drug going everywhere in the body, but most of the time we want it to target a specific part of the body. So some carrier prodrugs have been used for this. In theory, I haven't really seen it much. Oh crap! Let me go back here. And the one example the book talks about is the blood-brain barrier, and this image is on. Let's see, I didn't even write it down here. What am I doing? Let's see. It's on page 199, and this basically shows here, this compound right here has the prodrug residue on the left part of it and the drug residue itself on the right. And what the prodrug will do, it helps it cross the blood-brain barrier. We know it's extremely selective membrane and it's tough for drugs to get across that. So what will happen is this carrier prodrug will help it get across the blood-brain barrier, and then once it is across the blood-brain barrier, it will be broken down by enzymatic oxidation to release the drug by a suitable process, so then the drug can have its effect in the blood, or not the blood, but the brain. So it's cool because it can get across and then broken down to where the drug is just by itself, where you couldn't do that initially by the drug. So anyways, that is sections 9.5 through 9.8. If you have any questions,